Okay, I've got pickup truck now. It's a delivery van. It's I don't know what it is. Okay, we'll say it's a delivery van. Okay, a vehicle. This is a vehicle. I've got a magnet strapped on the back of it, kind of loosely with the rubber band. So I've got to be careful not to get this magnet too close. And I've got a magnet here that I think is aimed so that it repels. Just like, let's see. Yep, it repels. Okay. Now, if I release the card from here, goes that far. Can you find the acceleration? Well, we've done this, so we'll come to the conclusions. But if you're watching this and didn't see it, you should stop and think, can we find the acceleration here? Because first thing somebody said was, well, initial velocity is 0. I started to contradict that, and then I realized, well, no, that's the other situation. Clearly, the initial velocity is 0 when I release it, I'm releasing it from rest. And the final velocity is 0. Now, if you think acceleration is uniform, okay, you conclude that the acceleration is 0 and it never went anywhere. Okay, now that's a terrible contradiction because it obviously went somewhere. If I bring this thing up closer, it'll go even further. Okay, you don't want to analyze that motion when I'm coming up closer. There are approximations you can make, but that's another story. In principle, you could analyze it if you knew the exact equation of my motion. You could conclude the equation of this if you had sufficient information about the magnets. Okay, well, why doesn't the equations of uniformly accelerated motion apply here? Well, it's because acceleration isn't uniform. Okay. Why is acceleration not uniform? Because the force isn't uniform. The closer this gets, the greater the force. As it moves away, the force is rapidly decreasing. So you have, now I'll define my terms a little bit more as we go. That has to be the proximity, how far the magnets are, by how far the magnets are separated. Okay, and let F be the magnetic force. Okay, well, it turns out the magnetic force, we don't want to exceed a certain proximity because the magnet isn't securely fastened, it'll flip where the magnet becomes attracted. Okay, and that's not important at this point. And magnetic forces aren't important. The only thing that's obvious is the closer this gets, the greater the magnetic force. So that somehow the force does this. There is no formula for this force. You can't look up a formula for the force between these two magnets that works very well. You probably find a formula that sort of works. Learn multivariable calculus and model these things as an assortment of dipoles. Yeah, but you really don't want to do that, even in a multivariable calculus class. It's pretty complicated. Although you might understand it in principle, you don't know what a dipole is yet. So, yeah. Just telling you that it could be modeled with reasonable accuracy. You would want machinery to do the integrals. You don't want to do those integrals. You can't do some of those integrals. Impossible. Okay. You do the integrals by approximation, which is the way most integrals in the real world get done anyway. Because you don't have nice functions that you can find out derivatives of. Okay, or derivatives of. Okay, well, I have. So now my main point here is not to talk about all those details of the force, but I think they're interesting. And they kind of frame what we're trying to do. Okay. The other thing that is going on here is, okay, well, this thing speeds up. And then it slows down. Board there, so it slowed down a little faster. That's some extra friction there. And of course, friction is the key. And we saw that everybody. So yeah, there's friction. So there's the force of friction. So you got the magnetic force and you got the friction force. It's a force of rolling friction on the wheels. Turns out that the force is about 2% of the weight of the vehicle for good bearings for your car. Almost always close to 2%, mainly because of the way rubber interacts with the road. Also somewhat with your bearings, but most of it's the flexing of the tires and saps energy. Okay. And I mentioned that, we analyze this by energy. We bring the thing close, there's a potential energy. That's at the expense of Cheerios in my bloodstream that give me energy. Okay. So as soon as I recover from the effort, I can release this thing that's too close. There it goes. But it gains some energy, and its energy of motion, which we call kinetic energy, maximized somewhere around here. Then it started decreasing. Friction sucked the energy out of the system. So we got energy. I went to all that trouble, expended all those Cheerios to bring the thing closer. It all went to waste because friction sucked it away. But it wasn't totally wasted because the car's a little ways down the road. Okay. Well, then I got to pick up the magnet, which if you scale this up to real cars and stuff like that, it'd be heavy magnet. Okay. Now the frictional force, we model it as being more or less constant. In other words, we assume it's constant. That's the first approximation. There are higher order terms, just a linear term. Okay. But we don't know what they are until we measure it for a given vehicle or given system. So we're just going to assume we have a constant. Force of friction. Okay. So what's the net force? Well, the net force at every point of this graph is going to be this far below this. Okay. When is a force zero? Let's discuss that real quickly. Just when is the force zero? Okay, so somebody said the forces should be equal. I said, if they're equal, then you got twice as much force. Okay. And then said, not equal in magnitudes. And yeah, okay, that's good. You say a little more, and then I just whispered it, equal and opposite. Okay. They got to be equal and opposite. Then they would add up to zero, and your net force would be zero. Then I asked anybody to come up and point to the point on the graph where they're equal and opposite. Then first point was here, and I said, no, that force is really tiny. This force is much bigger in the opposite direction, but they aren't of equal magnitude at this point. Well, that's because the person who's doing this kind of gets to maybe this for the x-axis. Okay, this is the x-axis. Should have used different colors, but there they are. Okay, and then pointed to this smudge on the board, and that's a pretty good smudge. Okay, so at this point, the claim is that the forces are equal and opposite. I can label this the x at which forces are equal and opposite. Yeah, so that's pretty good. Let's see, this force is about this big, and this force is about this big. It's pretty close. Okay. Another method for doing that would be to draw a phantom frictional force. Let's see. Well, this would be negative force of friction, and you would get an intersection point here, but I actually like this one better. It's more accurate than my drawing, but you can do that. Okay. Where the magnitude's equal because they have opposite signs. So just flip this graph. You see. Okay. Now, that force always is the sum of all the forces. Okay. Now, there are other forces acting on this. You know, you've got the gravitational force acting downward. Why doesn't the thing fall? It's because the weight of this thing slightly compresses and slightly maybe bends its board a little bit. Okay. Then you have essentially an elastic response of the board trying to decompress and unbend. It exerts a force up this way. It's called the normal force. Well, let me stop and draw a diagram. Needs to be purple. It just hasn't. It demands to be purple. Okay. Here's my X direction. With my Y direction. Here's a dot at the origin that represents this delivery band. You can think of the dot as being at the center of mass and the center of rotation, whatever, of the delivery band, depending on the situation. Okay. You have gravitational force. Okay. You have this elastic force. I want to use the word reaction. We want to confuse reaction. Okay. Let's say the elastic response, not reaction. Reaction has a very specific meaning by Newton's third law. We'll talk about that. Elastic response of the surface is a gravitational force. I'm going to put an arrow over this force and an arrow over this force. And then there's another name. Often, I think your textbook will use a capital M, which is easily confused with Newton. So for right now, I'm going to call this F. Norm. The way this thing compresses, when it decompresses, it wants to move the object that's compressing it directly away from its surface, meaning at a perpendicular to its surface. If this thing bends a little bit, when it unbends, the unbending will push it perpendicular to the surface, meaning, among other things, that if this thing's on the downhill, then the elastic response or normal force is in this direction, not straight up. Normal forces are not always straight up, they're perpendicular to the surface that exerts them. Okay? Now, this is all really important stuff. I recommend you listen to this. You take a few minutes and get this introduction to forces, okay? I'm covering a lot of ideas here that your book will make more explicit. But if you have those ideas in your head, make notes on it, things like that. And you probably don't have time to make notes. You can if you wish, if that helps you understand. You might be better off to sit back and absorb it and then look at it, because I'm going through this pretty fast. It shouldn't be a long part of the video. Okay. Well, okay, so here's your normal force. Again, normal forces are perpendicular to the surface. I'm not going to write that down. I'm just going to say it, but kind of sort that idea in your head. And you know, what did I say about that? If you view and listen to the video, that would be a good point to stop and make yourself a note that the normal forces are perpendicular to the surface, and it's because the compressive forces decompress perpendicular to the surface, and elastic forces, the bending, unbends perpendicular to the surface. I've got a very simple demonstration of that with the music. We'll see that later. Okay. So you got the normal force and the gravitational force. Okay, well, we have Newton's second law. F net is the sum of all the forces. Okay, now you can make yourself a note that that means the sum of all the forces, because I'm not going to take time to write that out. Okay, and F net equals mass times acceleration. Okay. Furthermore, you'll understand some linear algebra. F net in the x direction equals the mass times the component of the acceleration in the x direction. And you're used to acceleration components in the x and y direction because you've been doing projectile problems. Okay. And F net in the y direction is the mass times the y component of the acceleration. I can get back to more fundamental principles. I go back to the Lagrangian and derive it. Well, probably not off the top of my head, but you probably never see a Lagrangian unless you go into some really advanced stuff. Okay, so I don't need to talk about it. There are other ways to explain. Simply that the force in the x direction is independent of the force in the y direction. Force in the x direction accelerates things in the x direction. Force in the y direction accelerates things in the y direction. And if you got a z direction, force in the z direction, component of the force in the z direction, accelerates the mass in the z direction. It's that simple. And that's all I'm saying. Okay. It also now the situation we're talking about, it's only x as far as the motion of the car. But you have y components. We don't have a z component. We set our x and y axes so that x is along the incline and y is perpendicular to the incline, forming a right-hand coordinate system where if you take your fingers and turn the y-axis to the x, your thumb points outward rather than in. Okay? You see the right-hand rule? I think you did. You certainly would have linear algebra when we talked about cross product. So something everybody should be familiar with. Okay, so we've got normal force, gravitational force, and also the acceleration in the y direction is 0. Okay, so what's the force in the y direction? Mass times the acceleration in the y direction is mass times 0, which says here net force in the y direction is 0, which says that these forces have to be equal and opposite because there are no other forces acting in the y direction. And in this lab, there are gremlins and eggs are forced, but we'll ignore that. Okay. If something goes wrong, it's the gremlins exerting some unpredictable force. It's always my excuse. Something always goes wrong. Okay, well, there we have it. Now in the x direction, what do we got? Well, we got a force of thing. Okay. Now this is variable. So just some arbitrary magnetic force. It says F sub mag and this is a diagram for the early phase of this motion. Okay, it's like the diagram when this force is a little more than twice as big as this force. So 2 of these would be up here. So that's kind of almost the initial point. Okay. Now, does that make sense? Okay, so what I'd like everybody to do is draw me a force diagram for, let's say, we go to college. Let's just say for, let's just say that at this point, this is the diagram. We notice that the magnetic force is bigger than the frictional force, and this is bigger than this. Okay, so what's the force diagram going to look like here? And what's the force diagram going to look like here? Just draw me pictures. And vertical forces aren't going to change. All the forces that change are in this direction. And only one of them changes. So you ought to be able to draw three forces that don't change and then slap in the fourth force, if you can identify which it is. Once if you're understanding this, so right now you're trying to do that. Okay. Okay, so we got, I think we got pretty good graphs. I would say for the second point here, and my axis is already tilted, pretend that they're horizontal and vertical. You're going to have these two forces, and you can label them, and you should, after you draw them. These two forces should be equal and opposite. Okay, they should have the same length as best we can estimate that. And what I saw was it all looks pretty plausible. And you know, mine's not great. This one's somewhat shorter than this one. It should be okay. So now we have the frictional force, which is same as this. So these three forces are the same. Diagrams shrunk down a little bit. They don't have room. But what happens to this one? Well, at this point, it's equal and opposite to the other one. So that's what everybody, I think, heard. Okay, so that's for this point. Now for the third point, that most of you through magnetic force may be a little too big, but as long as it's clearly smaller. That magnetic force looks like it's just about a third as big as the friction force. It's getting down pretty close to the x-axis. Not being critical, just to point out. So long as it's considerably shorter, I'm pleased. And I think it was in every case that I was able to see. So, you know, this has to be pretty short. Okay, so I just drew a real tiny arrow here. You can't even hardly, you can even hardly see it. It would be about out to here on this diagram. On this small diagram, it's almost invisible. Okay, not really. You can see it if you have good sharp attention. You can draw it. But then that would be for this section. Okay, so now what's happening dynamically, that is, as time goes on, what's happening? Well, let's add a picture for the net force. Okay. So if I add this force to this force, how do I add vectors? I add them head to tail, right? So adding head to tail, I have this vector and then this vector gives me the vector that represents my net force. That would be this one. It's supposed to be equal and opposite to this one. I didn't make it long enough. Okay. Should have come back to about here. So this should be a little shorter. This should be a little longer. But you get the idea? Then I offset them a little. I can't draw them all right on top of this vector. You wouldn't be able to see it. So we understand that all these vectors are right on top of each other. All right. Well, show me the vector diagram, this situation, and the net force. And show me the vector diagram for this situation, and show me the net force. Okay, this is a pretty simple situation, but don't shortcut it. You know, when I draw 3 vectors here, you should draw 3 vectors, okay? So here, 3 vectors would be this one, and a 0 vector, okay? So here, and you can't really draw a 0 vector, but you've got to indicate clearly that you're adding 2 equal and opposite vectors, and then you can conclude this from the picture. For down here, just make sure we've really got the idea. And you know, I'm stressing we want to be really precise about this. I saw an article once in a scientific, a physics journal, okay, where there's a disk like a flying saucer, and on one side it's got a jet. So that jet both propels the thing in whatever direction it does, but also rotates it so the jet keeps rotating, okay? A majority of PhD physicists couldn't draw the free body diagram for that, okay? Neither could I. I didn't try that hard. And maybe I'd have done a better job than a lot of PhD physicists who haven't thought about free body diagrams for a while. As engineers, you got to think about free body diagrams to deal with forces, okay? You can never forget them. A physicist that's working in particle physics doesn't have to worry much about rotation, okay? They kind of have an excuse, but they ought to remember their freshman year, okay? They got a PhD in physics, they're probably smarter than I am. Almost all of them are, but there are a few dumb ones. Okay, well, anyhow, I'm not dumb. So I want to stress the details. And then some you left out details. Okay, as a matter of fact, most of you left out some details. So on the third diagram, it looks like this. And we know what the vectors are, so again, I'm not going to label them. Looks like this, right? There's one of 2 ways to draw this. 3 ways, actually. I'm going to draw it this way. Here's this vector, okay? And then take this vector and add it head to tail. So here's this vector. So here is the result. If I don't see all 3 vectors, I at least want to see 2. Okay, and by that I mean, if you've got this, and this, and this, you could sort of implicitly say, okay, I've got this one, there it is. Okay, then I've got to do this one, comes back this way, which gives me this, and here's my diagram. I kind of prefer to see all 3 of them to emphasize what you're doing. But if you line the initial point of this vector up with the terminal point of this vector, I know what you meant. Okay. And that's acceptable, although I kind of prefer the other. Wouldn't penalize this. I think you're less likely to make a mistake if you do this. Now, you're not likely, after you've done a couple of these with nice right angles and everything, to make a mistake at this point. When it gets a little more complicated, if you're not as specific as you can possibly be, you're going to be at risk. Okay. you're going to build whatever you're building falls apart. Hopefully after you're dead, so nobody can blame you much. Okay, but hopefully that's a long time in the future. So it lasts a long time, it's pretty well built, but you screwed up one free body diagram and eventually it collapsed and hopefully nobody was in it. Okay, make sense? Be meticulous. More important for engineers and physicists, but it's important for physicists too. You don't understand it if you can't do it meticulously. There's no reason you can't do this. Well, okay, now, what's all that say about this thing? Well, it says that, well, here's our magnetic force. Here's our friction force. Know what these are, we all play them anyhow. And this is supposed to be horizontal. Still, your net force is going to be this much lower at every point than this force. So you come down this far here, you come down the same distance here, you come down here, and so you get out to about here. And then the force starts going negative by the time you get down here, pretty close to this. So here's your net force. Now, at what point does the direction of your acceleration change? Let's discuss it for a second. Okay, immediately got the response here. And this, of course, reminded me of the intermediate value theorem, okay, which assures that if you have a continuous force and it's positive on one side, negative on the other, that'll be zero somewhere in between, maybe at many points. In this case, only one point because the function is monotone. Okay. And then I commented that if you have electromagnetic forces acting in this, you cut off a force that essentially disappears more or less instantly. And if you have the instant model, you have a force that comes down here and then suddenly appears down here. And it's never zero, it goes from positive to negative practically instantaneously. In fact, there is, I can't think of a way, at least not an electromagnetic force, that could instantly go to zero. Okay. It kind of has to fall through zero, but it happens so quickly that it might as well be instant. That's just, and then look up the intermediate value theorem, how it's proved. Gives you better insight into functions and so forth. That's not a requirement. I'm not going to test it, but just some advice so that you keep your calculus up at a certain level. I'll also comment that I picked up a statistics book last night, and I can't stand to read statistics books because they're not rigorous. Well, this one does all the calculus. Actually, multivariable calculus. Just pretty cool. Okay. I refuse to understand some distributions until they're well defined and until you do the calculus. I don't even want to talk about them. I know what the questions are and they arise in lab all the time. Now we're not going to do multivariable analysis, but we are going to do some statistics with our data. Just another slide comment. Okay, now back to motion. Well, then this means that the acceleration has the same curve, just with different numbers. Okay, so okay, so this curve is F net. This curve is the acceleration. Which is F net divided by the mass. The more mass you have here, the less response you're going to have to these magnets using the same two magnets. So for example, I could set a piece of iron on top of this thing, which would maybe triple its mass. And then see what happens with the magnet. But we're likely to do that in lab and get data. Okay. So this system is one of my favorite things because it costs like $1. Okay. If you include the magnets, maybe $2. And we get a lot of stuff out of them. Because these things they're hot wheels, they have really pretty good wheels. Okay. Well, let me now back up a little bit and ask what was the acceleration of that cart as I just pushed it. You can look at the video, see how far the cart went or how far it cared to go. You need to make estimates that their cart is about 2.5 inches long, about 6 centimeters long. See how it fits. Meter stick up, down. Gotta remember not to be plots for a few days. Okay. About 7. Okay. But this thing's 7 centimeters long. Well, let's just poke it again. Starts here. Its length is about this. So that's about 7 centimeters. And I poke it. And of course, acceleration is not uniform after it hits the picture. Let's see if I get it. You didn't hear a sonic boom, did you? I've got to control my speed because I've been sued before. Okay, well, I'm lucky I didn't cut myself on this thing, but I know it's there, so kind of what's out there. Ready? Okay, it pretty much came to rest before it fell off. If it came to rest here, how long did it take? Were you timing it? Do you remember? If you counted 1,001, think 2 seconds, think 2 seconds. Okay, how far did it go? Well, what about 1, 2, 3, 4 of these? Okay, so maybe 30 centimeters in 2 seconds, average of 15 centimeters per second, initial velocity 0, so change in velocity 30 centimeters per second. In 2 seconds, it gives you 15 centimeters per second squared acceleration, which is about the acceleration people who did the experiment and did the calculations got on that ramp. They didn't get it from everybody, and got hassling about that again. That was clearly a sign. I think it was written down there. Okay. So anyhow, you can make an estimate. We do ballpark estimates in lab. Just say, okay, I think it took about 2 seconds. Here's how I get it. Now let's go ahead and see if we can time it using Audacity, using 3 significant figures rather than 1, so we don't have all the uncertainty in our results. Okay. That's a little difficult to time this though using Audacity because it doesn't make a noise when it stops. And you don't want to stop it with something that does make noise because that you don't know what its velocity was at that point, right? So maybe it's a little more useful to put this thing in a ramp and measure its acceleration. So it does make noise. Click something when it starts, you hit something to start it, and have it run into something when it stops, because Audacity shows you a very clear spike. There are other ways to time it. I don't think you can beat Audacity for accuracy. You can, but not with anything we can afford in this lab.